In this video, we're going to talk about section 2.3, properties of functions. Before you watch this video, you should definitely read the definitions of local minimum and maximum, absolute minimum and maximum, because I'm going to try to draw a couple of functions that might help you kind of keep these ideas straight. Okay, so here's a function, we'll call it f, and I'm not going to put any actual values on it. I'm just going to draw what it might look like as far as values, high values and low values. So let's say we have this continuous function. It doesn't look very good over here. I'm going to redo, I think, this part of it. There. Let's redo the whole thing. All right. There's going to be a little hole in the function here. So, boop. Ugh. Oh my goodness. This video is going crazy. And I want to actually redo the end part of this here. Let's put it much higher. Okay, so let's say we have this function. It's continuous, meaning that you could draw it without lifting your pencil. Clearly I lifted my pencil and that made things a little bit strange. But let's say that, it's all connected, except for this little circle and this little circle. There are some holes. Okay, and we'll call this guy f. You might be wondering about some of these values and whether or not they are local mins, local maxes, absolute mins, or absolute maxes. Let's start here over on the left. This point here we would call an absolute maximum and a local maximum. I'm sorry, not maximum, minimum. Maybe I should start this whole video over again. I'm not going to do that. Absolute minimum and a local min. It's an absolute minimum because it's lower than any other function value on the function for the entire interval on which f is defined. And it's a local minimum because there's these parentheses I'm using to signify that there's an open interval where all the values of f in that interval are larger than the value of f, or the y value, at that point. It doesn't matter that the function doesn't have any values on the other side. At whatever x this is here, the function doesn't have any values to the left of that x value. That doesn't matter because the values of the function are higher everywhere that they exist in that interval. Now let's look at the next from left to right, here. Right here, f has no function value here at all. So there's no function value, or y value, or an x that gives us that y. So right here, we cannot call this a local max, even though you might think it looks like one, because f is lower in all of that. The values of f are lower at all x's around that, but there's actually no value at that certain point. So if it's not a function value, it can't be any kind of maximum or minimum value. We could say the same thing too about this endpoint over here. There's no function value here. So this point is not again, not a local min, a local max, an absolute max, or an absolute min. You might think of it as an absolute max, but it can't be because it's not even a value of f there. There's not even a value of f there. In fact, this function f has no absolute maximum because the values, the y values, as x gets larger and larger, they approach a number, but they never really attain it, that value. So there's no maximum. It just keeps getting a little bit bigger and a little bit bigger and a little bit bigger, but it's not a value. This point here in the middle, this is nothing. It's not an absolute, it's not a local min or a local max, because around this point, their function values to the right of the point are higher than the point, and to the left of the point they are lower. And so what that means is that it doesn't fit any of the definitions. We do have a local min at this point, because all function values to the right and the left of that point are higher than at that point specifically. All right, let's look at another one that has some interesting things going on. This one's a little bit simpler to draw, so it should I shouldn't have to redraw it 5 times. All right, and let's consider all of these points. This one here would be a local max, because although in the little interval around it, the function, if we call this f, has values smaller than the function value at that point, there is a spot, if we look over here, where the function values are higher than that point. So we can't call it an absolute max, even though it's an endpoint. Up here, though, we can call this an absolute max. In fact, it's a local and an absolute max. It's a local max and an absolute max. Because for all x in this interval, if I think of this x value c, and the function value here will be f of c, we can say for all x in the interval near c, f of x is less than f of c. The entire function for all of that, for the local. And for the absolute, for on the entire closed interval, from, let's call this b, from b to c, f of c is greater than f of x for that entire interval for the entire function. And then we have this little point down here that we would call a local min or minimum, but it actually ends up also being an absolute and absolute minimum, right? Because it is the lowest point on the graph. Okay, by looking at these two things, we can maybe make two little conclusions. All absolute extrema, here's a new word, extrema, which means min or max, it's the plural of all of those, are local as well. So if you have an absolute extrema, then you get a local extrema. But only some, however, local extrema are absolute. Are absolute as well. Only if they are the lowest or highest function value for the entire function. In calculus, there's a really, really important theorem that I'm going to just tell you a little bit about right now because it goes along with exactly what we've been talking about. It's the extreme value theorem. It says that if a function f is continuous, and right now we'll say you can draw that means you can draw without lifting your pencil, on some domain from A to B, and notice this domain is including A and B, then we can say always that f has an absolute max and an absolute minimum or min on that interval. So this is a theorem that guarantees that any function that's continuous on an interval, there's no holes, you don't pick up your pen, it's guaranteed to have an absolute max and an absolute min. I'm going to take a look at one that kind of confuses people sometimes because you think, wait a minute, what's going on with that? Let's say our function f is constant for a bit and then ends up, oops, I'm sorry. I want to make it lower. And then ends up going like this. And we'll say that this is A down here and that this is B. So notice it's continuous, it keeps going from A to B. Okay. There's a point down here somewhere at C that would have function value or y value f of c. I think it's pretty clear that we can see that f of c is its local, it is local, but we're talking about absolute right now, is the absolute minimum value. Okay? Now because this is continuous and its endpoints are included in the domain, it should have also an absolute max according to the extreme value theorem. Okay? So, if we look here on the constant value, we could call this value f of a, right? This, let's say we have a point called, or an x value d here. This point is at d comma f of a, no? And this is a comma f of a. F of a seems to be the highest value of the function, and it is. F of a is the absolute max. It happens to be the absolute max on an interval A to D. So something interesting to note when you're thinking about maxes and mins and extrema is that we're not really interested in points, we're interested in y values or function values or heights, you might think of it. So an extreme value, an absolute max, min, or local max or min is a y value. It's a height of the function. It doesn't matter if it's 1 point or many, many points.